Swayam Prabha. Digital India. Educated India.
I welcome you to this module of flow through porous media. What we are discussing was miscible displacement. That means already a fluid is present in the porous medium and now we are injecting a fluid which can mix with this resident fluid. So, in this case inside porous medium how the mixing takes place, that is something we want to understand. So, before we get to this, first we are trying to understand how the mixing takes place in a capillary, and so we were discussing about Taylor dispersion. That means when the velocity profile itself is not uniform, then that can contribute to the mixing. So, how this sort of how this mixing takes place. So, let us see here. We have what we discussed earlier is that in a static system, this is the equation we had derived. We had arrived at for the static system. This is the equation we arrived at. C1 is equal to C1 is a function of z and t, position and time, and this is given by m, total amount of solute one places at z equal to 0 in terms of kg of solute, and as a function of z and t. And what it is, when we are talking about Taylor dispersion, or everywhere you will find that we want to stick to this particular form of equation, so that at any time we can compare. See, here we get a field. What is the field? That I said that I have introduced we have introduced a Dirac function, and we expect that this would diffuse like this. So, with time we expect that it would take this kind of shapes. So, what we did here is, suppose I say that the concentration at any location, it will increase with time like this when z is greater than 0. So, now if we change, let us say diffusivity d, what would be the effect? If d is increased, we always know that the broadening will be faster, because it is diffusion coefficient. Something has a higher diffusion coefficient, that means it mixes faster, right. Something has a very low diffusion coefficient. So, though they are supposed to be miscible, so I have one liquid, another liquid, we put them side by side, they are supposed to be miscible. So, they will mix if you leave it for a long time, but it will take long time to mix. So, diffusion coefficient is that, and diffusion coefficient is that characteristic parameter which tells you that how fast it will mix, how fast the molecules will diffuse. So, naturally if d is increased, I can see the impact here. So, now suppose Taylor dispersion with all the equations they have considered and everything, if they arrive at a very similar equation, but not d, instead of that some other parameter, some other clubbed parameter, I mean it is, say, let us say instead of d, they are talking about, I mean I am giving you an example, let us say r naught square v naught square by 48, some lump parameter I have, all other terms remaining same, I have a lump parameter here. So, in that case we know that if we change r, what would be how the lump parameter will change, and if the lump parameter increases, we know that it will have a very similar, you will have a very similar experience here as when the diffusion coefficient increases. So, Taylor wanted to, I mean in this entire analysis, Taylor wanted to stick to this particular form. So, let us see what they have done. Now, one thing we have also pointed out at this time is that if this moves, this entire Dirac function, that is the pulse that we placed, if this moves at a constant velocity u bar, so the center of this pulse. So then we can still find out a concentration C1 as a function of z and time, space and time, but only thing is there has to be a correction, z minus u bar t whole square. That correction has to be there to take care of the moving front rather than a static front. So now we had talked about the stellar dispersion. We have already talked about this governing equation. So we said that this governing equation includes a radial diffusion, that means diffusion in this direction, radial diffusion in r direction, and convection in z direction, that means flow is continuously taking place in this direction. So some with the flow, some mass, some molecules that are put into this Washer-Schreiber differential element, some are leaving because of this flow. So how much is the accumulation, that is accounted in this. Okay. This was not important when you have a uniform velocity profile, but these are important when you have a non-uniform profile. So with this and we have talked about the boundary initial and the boundary conditions. Now at this time we must note one thing is that when it comes to a capillary, what we see at the outlet, when it comes to a capillary, what we see at the outlet is not the concentration as a function of r, that is not possible for us to measure. Think of this, I have a capillary. If you want me to find out, if you want me to prove that this equation is valid, so for that what we need to know is, I have given you already a Dirac function, I have just introduced a pulse of a salt or pulse of a dye, okay. And then at the outlet I am measuring the concentration profile, but concentration profile with respect to r. See, earlier we did not have a concentration profile with respect to r, mind it. When you have a static system just simply traveling at an average velocity u bar, no uniform velocity profile, that means a front is all uniform. So, I mean it is more like a plug flow. So, at that time concentration was only a function of position and time. But here we have an added problem that this concentration is a function of radial distance, axial distance z and r, two axes, as well as time, because we have function of r, function of z and function of time. So, concentration is a function of r, z and time, but frankly speaking we have no way to measure concentration as a function of r, because these dimension we are talking about is to the order of 1 micrometer. So, within 1 micrometer, if we it is next to impossible finding out the concentration at various points, I mean in our traditional way of doing things. So, rather what we do is we can collect slices of so whatever is arriving at the outlet, we can collect the slices of it and mix those slices. So, I am collecting, let us say, this fluid and I am getting slices. So, these slices, and if we get these slices, they are all well mixed, because I am collecting it in a cup. So, one cup for this, another cup for this, another cup for this, another cup for this, and this cup, whatever is collected, they are all mixed up, and that concentration we can measure, okay, by putting it in a spectrophotometer, UVV spectrophotometer, or measuring the refractive index, or doing some other way of doing things. But I have to collect it in a cup, and there has to be some substantial volume to do this measurement. So, obviously what we are doing is, so we said that we had stretched the pulse, like this. So, essentially, so at the outlet this stretched pulse will arrive, maybe they will be more diffused, maybe it is more diffused here, maybe more diffused here, because of the diffusion, because already I said there will be a radial diffusion taking place. So, now when we are collecting this, I am collecting it in slices. So, this slice is 1, next slice is 1, next slice is 1, next slice is one like this. So, this slice I am collecting it in a cup and I am measuring their concentration. So, essentially we can get C1 bar Z, this is something which you can measure. So, basically this this concentration is averaged over all R. So, how we can average it? We can write this C1 at RZ is existing over this annular shaped area, right. Over this annular shaped area, this C1 is existing. So, if we multiply this C1 with 2 pi r dr, 2 pi r dr is what? These cross sectional area, this hatched area is basically, you already know, it is pi of r plus dr whole square minus pi r square, and if you ignore pi of dr whole square term because dr is small. So, you end up with this area as 2 pi r dr. So, what is the volume of this washer shaped element? This volume of the washer shaped element is 2 pi r dr multiplied by dz. So, 2 pi r dr dz. So, 2 pi r dr dz. So, what is this? 2 pi r is in meter, dr in meter, dz in meter. So, this gives me meter cube. This is the volume of this washer shaped element, this entire element. This entire element will have a concentration of C1 because C1 is applicable, C1 within bracket R and Z. That means, around R a differential area and around Z a differential area. So, this is the differential volume that you can construct around R and Z. So, this is where C1 is valid. So, this is unit of volume in meter cube, this is in kg per meter cube. So, kg per meter cube in meter cube, this gives me kg. So, all such annular shaped elements, if you integrate from 0 to R. So, what you do is then one thing you can note here is that you do not need to work with this dz because this is the concentration of one different for this differential volume, and then you have the total volume of this system is basically pi r naught square dz. That would be the volume of this whole so differential if you extend it. So, for the entire cross section. So, this dz you do not have to bother, and this numerator has to be integrated from 0 to capital R. So, that is 0 to capital R 0. So, that is exactly this average concentration. That means, total mass contained within these washer shaped element divided by the corresponding volume. So, this is the average concentration. So, when you collect this in pieces, you are collecting the average concentration. Now, what Taylor has shown is Taylor has solved this equation, and Taylor has shown that the C1 bar as a function of z, that is written here, is m divided by pi r naught square divided by square root of 4 pi E z t e to the power, this is exponential term, e to the power minus z minus v naught t whole square divided by 4 E z t. Achha, v naught is same as the earlier we had talked about u bar is same as the average velocity. What is average velocity? Average velocity is average velocity that we have studied in the context of flow through a pipe or flow through a capillary when we define friction factor. There we have arrived at this particular expression, and there this is that V naught that we considered here, which is same as u bar, which we considered in case of a uniform flow where the velocity is uniform. So, that so it is same as the average velocity. In case of uniform velocity, that is a single velocity, there is no other velocity, whereas in case of parabolic velocity profile, this is the average velocity. So, this is how. So, now this equation looks very familiar to us in the sense that This equation is basically m by a was pi r naught square. This is already we know. Square root of that time we had 4 pi dt. In case of static system, you recall it is 4 pi dt. Instead of d, now we have a term which is Ez, which is different, but that we will look into. But 4 pi dt e to the power, there also we had the same thing, minus z minus v naught t. We can very well now relate. It was originally in static system, it was e to the power minus z square by 4 dt. Now then next what we did is we said, okay, we have a moving front, but uniform velocity. In that case we talked about a moving coordinate system, and instead of z we had subtracted this v naught t. So it became z minus v naught t whole square by 4 dt. And now in this, but that time it was z minus u bar t, because there was only one velocity, single uniform velocity. Here in this case, in case of a Taylor dispersion, we have the average velocity. So average velocity we can still relate. I mean, average velocity means that the center of this pulse somehow is also moving at. So that is basically a reference system. So z minus v naught t whole square by 4 Ez t. So this Ez is different. So Taylor is successful in bringing this equation to the same form as we had seen in case of static system, or the variant that we have seen in case of moving front with uniform velocity. So, and now what is Ez? Taylor found that this Ez is the dispersion coefficient. This is called dispersion coefficient, because now we are talking about dispersion. It is not diffusion, because we have a flow plus diffusion. Flow has already put his signature here by stretching the pulse itself, and this dispersion coefficient is r naught v naught whole square divided by 48 d. So, what does this mean? This has some amount of implications here. What are the implications? Ez is equal to r naught v naught square by 48 d. This you have to look at very carefully, because we said that we have a velocity profile. V naught is the average velocity. So v naught is equal to average velocity. Average velocity, we have a parabolic velocity profile. So we have maximum velocity at the center, and then we have velocity at the wall is 0. So we have some average velocity which is v naught. R naught is the radius of the capillary. Radius of the capillary. And the d is equal to diffusion coefficient. These two terms are interchangeably used. Sometimes we call it diffusivity, or we call it diffusion coefficient. So it is one and the same thing as far as this lecture is concerned. So earlier it was d. Earlier this term was d. This term was d. Now which we are calling it, no, it is not d, it is Ez. So whatever effect the d had, the same effect now this Ez is putting. So that means what was the effect of d? I had this Dirac function, and when d was higher, I would have expected this to be stretching faster. Okay. So it is spreading faster. So this was the profile at that time. So now Ez higher means this would be the same thing to this concentration profile, right. So if Ez is higher, there would be more stretching. So what will make the Ez higher? Ez will be higher when the velocity is higher. When the velocity is higher, the Ez will be higher. And when R naught is higher, the Ez will be higher. So that means when we are working with a higher velocity, we expect this dispersion coefficient to be higher. That means the spreading would be higher. So, that means when you submit this Dirac function to a parabolic velocity profile, now we have enhanced, now we have more diffusion taking place, because now this pulse has been stretched like this. And so, earlier it was just one single one, and then there was some axial diffusion was taking place. Now it is not, we are not, you have ignored axial diffusion, but now we are talking about a radial diffusion. So, we can see here that now this diffusion is taking place over this whole slug, okay. And then we will be chopping, when we are collecting the slices, we will be collecting slices, this slice, then this slice, then this slice, like this, okay. So, when we put it in mixing cup, this will be mixed anyway. So, think of it that when V naught is increased means you have this is also getting stretched more, this one is getting stretched more. So, you are allowing this front to be, even if the mixing is not that much, but this front is anyway stretched. So, as long as we are collecting these samples, we will continue to see the effect of mixing, because this front has been stretched much, right. So, that is why I can see the effect of R naught and V naught coming in, because R naught and V naught, they are essentially stretching this particular profile here. And diffusivity is, now it is the inverse function. You can see it is, this Ez is inversely dependent on diffusion coefficient. What that means is that when D is higher, when the diffusion coefficient is higher, the actual tailored dispersion coefficient is lower. So, that means when D is higher, when diffusion coefficient is higher, the dispersion is not happening that much, because if the diffusion coefficient is lower, you are stretching it this way. So, you can let it, you can continue to stretch, and you can make it a the footprint would be over a much larger length. Whereas, when the diffusion happens, then this slug gets contained within a shorter distance. So, the footprint would be smaller. So, these are very unique dependence. One can note that by virtue of this, one can see that the same system, we are working with a uniform velocity profile. In that case, we see that it is simply the diffusion dominates. If diffusion coefficient is higher, means the spreading would be more. Whereas, in case of tailored dispersion, that means when the flow is not uniform, rather you are following a parabolic velocity profile, diffusion coefficient is more means stretching would be less. Sorry, diffusion coefficient is more means the dispersion coefficient would be less, and dispersion coefficient less means the total effect on C1 bar would be less. So, that means you will see less stretching if Ez is less. So, D increases means Ez decreases, and Ez decreases means C1 bar decreases, because Ez has the same effect as diffusion coefficient. So, this is something which one must make note of while working with this scheme of things. Now, we must note here that the purpose of this entire exercise is, so let us before moving, I mean, in fact, our next step would be, so with this understanding of tailored dispersion, our next step would be to study the diffusion of a step in a static, diffusion of a step, mind it. Next step would be diffusion of a step in a static system. So, diffusion of a step change, that means earlier what did we do? Earlier what we did was diffusion of a pulse. So, all along we have been talking about a pulse. So, initially this is the Dirac function, and we tried to see that this Dirac function how it would feature. That means, it is something like you have a concentration, you have this capillary, and then you have given a Dirac function, and at the outlet. So, at the outlet what do we get basically? If we have a detector, let us say I have a detector which detects the concentration. So, what do we get at the outlet? At the outlet we will be getting concentration as a function of time. I mean, if you go to any detector, this is what you would get. With time, if you have a continuous flow is taking place and the detection is going on. So, with time you will get, so with time when you start, the concentration was all 0, and concentration was all 0 because it takes some time, and then typically around the residence time, we have already talked about the residence time, right. So, typically around the residence time you would expect, okay, a little bit before residence time you see start building this concentration, and maybe this is something which you are supposed to get. So, before the residence time is reached, you will get something at the outlet, and after you get there, after the residence time also something, and then it goes to 0. So, this is something which you get as concentration as a function of time. So, if you now you can convert this concentration, instead of time you can call this, instead of time you can call this also, you can plot this as a cumulative flow, where cumulative flow is equal to cumulative flow is basically equal to Q multiplied by T, where Q is the volumetric flow rate multiplied by T. So, if the flow had taken place over say 10 minutes, so over 10 minutes whatever in meter cube per second you have. So, if you take the product of 10 into 60 seconds and so many meter cube per seconds. So, meter cube per second into seconds, so you get meter cube. So, cumulative flow means so many meter cube has flown through the system, right. So, this is the cumulative flow. So, at this cumulative flow it will peak and then it will go down. And how do you get this cumulative flow? This cumulative flow, this value, we said this is when we plot this, it is the same profile you get, because the x axis we are simply multiplying by a constant q, right. Earlier we plotted as t, now we are plotting it as q into t. So, it is just a q. So, q is just a constant because we are having a constant flow rate. So, the trend will remain same. So, now this was that time, it was the residence time. When we talk about this cumulative flow, this volume essentially, if you think of it, this volume is the pore volume. If you are working in a porous medium, and if you are working in a capillary, this is not in that case the pore volume, rather I would expect this to be the capillary volume, we can call it capillary volume. So, this much, this is the volume, this cumulative volume is basically represents the capillary volume. So, after you fill the after you inject one capillary volume, then only you can say that you got the peak. So, in before itself you got there would be the tracer would be registered at the detector, and then beyond this you will see that it will start going down, and at one point it is 0, that means all the tracer has gone out of the system. So, this is something which we have this is something which we have noted here. So, basically, so what you are plotting here is, so this concentration that we are getting, this concentration is basically this average concentration C1 bar. So, this concentration, because we are not getting concentration at different radial points, but we are getting an average concentration for this slice. As I said, we picked up slice by slice. So, this concentration is concentration of each slice. Okay. So, this is something which we can get at the outlet. So, now what we are going to do next is, we are going to now, instead of going by the Dirac function, we will place a step change in concentration instead of a Dirac function. So, we are not talking about Dirac function, we will do a step change in concentration, and in that case we will get at the outlet also you will have with cumulative flow you call it, or with time you call it, we will get also after some point we are supposed to get this step change, because we have to provide this residence time, or you have to at least flow the pore volume, then only there would be the breakthrough. And this breakthrough, earlier case as I said, we had a Dirac function and we found at the outlet it has already started spreading. Similarly, the step change also will not be a firm step change. Ideally, if there is no mixing, we would have expected a step change, but since there is mixing, so we would expect if this is the residence time or this is the pore volume, we see a change which is something like this. Step is now diffused, okay. Step is little distorted, okay. So, this is something which you would observe if we do a step change in concentration at the inlet. We will work on this further, and we will focus on if there are step changes, how if there is a step change, what kind of concentration profile you get, and then we will because you remember this expression is very important. This is the Taylor equation for Taylor dispersion and this dispersion coefficient, because this information would be used in case of step change as well. So, here at this point I want to close this lecture, and the next lecture I will continue with the theories or what predictions we can make for a step change in concentration at the inlet and extend this to porous media. So, that is all I have for this lecture. Thank you very much.